Hi, so we are now in chapter 11, where we're going to be talking about limits, continuity, and eventually the derivative. Now, the whole notion behind the formal definition of the derivative is as a rate of change instantaneously at a point in time. And it turns out that it's not exactly that easy to talk about what it means to be a rate of change at exactly a point in time. So, what we have to end up talking about is what happens as things change over increasingly small units of time, which means that we need to talk intelligently about what happens as things get closer and closer to some value. In that particular case, 0, but here we have some other examples. So, in this graph here, I have a function called f of x, and it's defined to be this curve before 3, and then at 3, it takes on the value 6, and then afterwards, it takes on the values of this second curve. So there are four things going on here. You have a value that the function increases as x gets closer and closer towards 3 from the left. This takes on certain values. As x gets closer and closer to 3 from the right, certain values are taken on. And at 3 itself, it potentially takes on a certain value. So let's go over here and ask ourselves, what's the limit as x approaches 3 from the left of f of x? What's the limit as x approaches 3 from the right of f of x? What's the limit as x approaches 3 period of f of x? And what is f of 3? Now, ideally, we want all of these things to say the same thing. But in reality, that's not always the case. And certainly, this does not seem like the drawing of an ideal function. So, coming back to our picture here, when if I follow an approach towards 3 from the left and I come towards this dot from the left here, it looks like those f values get closer and closer to the value 4. When I come in from the right, it looks like these values get closer and closer to the value 5. Now, when I talk about the limit as x approaches 3, period, um, because on the right it comes towards 5 and from the left it goes towards 4, it doesn't seem like there's a single value that I could point out and say, well, as things get closer and closer to 3, f of x is going to get closer and closer to this. There is no such number. So that limit does not exist. And finally, what's f of 3? It's 6. Right? So this is a very weirdly behaved function. It gets closer and closer and closer to 3, and it jumps up to 6 and immediately jumps back down to right above 5 and continue to go on its way there. But that 6 does not reflect either this limit nor that limit. So let's change this around a little bit. Let's say that instead my function looks like that, which means that at everywhere but at 3, it follows this curve here, and at 3, it jumps up to 6. So, as I come in from the left, these values seem like they're getting closer and closer to the value 4. As I come in from the right, these things also seem like they're coming closer to the value 4. And then it is okay for me to say, well, it looks like if I come in from the left or from the right, then I'm getting closer and closer to 4 either way. So that's one of our first facts is if limit as x approaches a from the left is the same as the limit as x approaches a from the right, and let's call that thing L, then the limit as x approaches a of f of x will just be L. But then of course f of 3 is 6 still, right? Just because everything's getting closer and closer towards 4 here, the way this function is defined, we still have a jump up here when x is 3. So the function that I had drawn beforehand and this function here both describe what we would call discontinuous functions. All right, those were both discontinuous because of this jumping behavior here. So what would it take for us to change that? Well, if instead of here, my function took on a value here, 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 those would all constitute some sort of weird jump, right? You would still want to head towards 4, but at 3 your function takes on some other strange thing. And that's no good. If you want this thing to be continuous, you want it to be a smooth transition. In other words, you want the function to take on that value that you're going to there. So in this version of the function, I don't even have to draw a dot there, I'll just do that. I'll say, okay, when x heads towards 3 from the left, it goes towards 4. Same thing from the right, it goes towards 4. That means the limit is 4, and 4 is actually the value the function takes on. Well, at that point, we say the function f of x is continuous at x equals a if and only if the limit as x approaches a of f of x is equal to f of a. In other words, the thing we would like the function's value to take on is the actual value that it takes on. So everything agrees with each other, everyone's happy and nice, and everybody's continuous. And that is, that's what happens with most functions, right? Almost every function we've studied up until this point, at least words defined takes on a value like this. If I come closer and closer towards something, I get closer and closer to the actual value that it takes on. So what we are going to be looking at in the future are functions where that sort of thing doesn't exactly happen, and it doesn't happen because the function's hard to define at certain points we would really like it to be defined at. And that's going to be the focus of the ongoing lectures.